Welcome to today's video. Today's video is for Advanced Geometry, Chapter 12, Section 2, Chords and Arcs. There's a lot of theorems in this section that we will be using in proofs, so I will give these names. First, we start out with a definition. A chord is a segment whose endpoints are on a circle. So if I put 2 points on a circle and I connect them, then that's called a chord. Now, after that, we have a theorem that it's one theorem, and you can use these in any order, and you can kind of mix and match them. And it says, within a circle or in congruent circles, if we have congruent central angles, then we have congruent chords. So if I add the center of the circle here, and then I connect the endpoints of that chord I made, then what I get is I get a central angle, and the central angle meets up on the circle with the endpoints of the chord. Now, if I draw another one somewhere else, and I don't want to make it on the opposite side, so I'll put it here, and I'll try to make it so it looks like it's congruent. So if these are congruent, then what I get is this chord that I'm going to make here is going to be congruent to the first one. So if I have congruent central angles, then I have congruent chords. And if I have congruent chords, then I have congruent arcs. So we can go out further, and if you take a look at the chord that I created, it also intercepts an arc. So this arc up here would be the same as the arc that's intercepted by the other chord, since they're congruent. So congruent chords also have congruent arcs. And then congruent arcs have congruent central angles. So that kind of gets us back to number one again. So we can go congruent central angles have congruent chords, then congruent chords have congruent arcs, and then congruent arcs have congruent central angles. I let you say that in any order. I let you go from chords to central angles, or from chords to arcs, or from central angles to arcs, or from arcs to central angles. And what we call this one is we call this one the central angle chord arc theorem. Okay, and when you use this, you can just call it the central angle chord arc theorem, and you can use it in any order, even including like the reverse of 1 or 2, or actually this should be 3. There we go. Okay, so that's the first one. The next one, within a circle or in congruent circles, chords that are equidistant from the center of the circle are congruent. And we also have congruent chords are equidistant from the center. So remember, we always have to measure from a point to a line in a perpendicular direction. So if I go back up to my drawing and I draw 2 chords again, and I'll try to make them look so that they're congruent, and then I put the center of the circle in here. If I want to measure the distance between the center of the circle and that chord, I have to do it in a perpendicular direction. So this would be perpendicular, and this would be perpendicular. And what this theorem is saying is, if the distances are congruent, then the chords are congruent. Or if the chords are congruent, then the distance to the center is congruent. Okay. So this one is called circle equidistant chord theorem. And as long as you have the word, I like the word circle in it, something about being equidistant in chords, that's fine. And this is one we'll prove in class. So notice what we're given, and notice that we are given that we have perpendicular distances. So we're given circle O, we're given OE is congruent to OF. So the distances are congruent. We're also given that they're perpendicular. That's going to be important so that we can measure perpendicular. And then we want to prove that the chords are congruent. AB is congruent to CD. So this one uses that theorem. What's the value of A? So if you take a look, we double check. Are our distance measured perpendicular? Yes, they are. Are they congruent? Yep, the distance of the chord is 9 and 9. And if you take a look at this chord, it's bisected, so the whole thing is going to be 25, which means this whole thing is going to be 25. So the answer is D. And then we have 3 more theorems. In a circle, a diameter that is perpendicular to a chord bisects the chord and its arc. So let me draw a picture of this one. So we have a circle, and a diameter has to go through the center of the circle, so I'll draw a diameter. And if it's perpendicular to another chord, then what this theorem is saying is that it bisects the chord, so these are going to be congruent, and it also bisects the arc. So if we take a look at the arc, these are going to be congruent. The next one says, in a circle, a diameter that bisects a chord that is not a diameter is perpendicular to the chord. So for this one, we have a circle, and we have a chord. And what we know is that it bisects. The diameter bisects it. Then it's perpendicular. So we know that this is going to be perpendicular. Now the reason why this doesn't work with 2 diameters is because we can draw 2 diameters and they don't necessarily, as long as they're go through the center of the circle, they don't have to be perpendicular. So this one only works if it's a diameter in a chord. In a circle, a perpendicular bisector of a chord contains the center of the circle. So if we need to prove that something is a center of the circle, this is a good way to do it. So this one is saying, in a circle, the perpendicular bisector of a chord, so if I start with a chord and then I draw something that is perpendicular and bisects, then somewhere on this line contains the center of the circle. Okay. And if we ever wanted to find the center of the circle, we could just do this twice. We could draw 2 chords, do 2 perpendicular bisectors, and that's going to be the center of the circle. Okay. So let's give these ones names. The first one, these all start out with circle. So the circle, and this is the diameter perpendicular chord theorem. Second one is the circle, and the diameter bisects the chord. Chord theorem. And the last one is the circle and the perpendicular bisector. Chord theorem. And the next couple days we'll spend some time using these. We will use them in proofs so that you can get more comfortable with them. So the last couple examples, a little algebra. So if you take a look at it, what we have is we have a chord and it's perpendicular. So if I want to find the missing length, this is going to be a right triangle. I know that if a diameter, so if I can that's going to be the diameter. I know that if it's perpendicular to a chord, then it bisects it. So I know that this is 7. And so what I can do is the Pythagorean theorem. So 7 squared plus 3 squared equals r squared. So 49 plus 9 equals r squared. Add those together is 58 equals r squared. R equals root 58. And it tells me to put that on my calculator, so I'll do it. And I get about 7.6. Look for units, centimeters. And for the second one, this one, if I follow that out, that's a diameter. It bisects the chord, so I know it's perpendicular, so I can use the Pythagorean theorem again. So I can say that 11 squared plus y squared equals 15 squared. So 121 plus y squared equals 225. Y squared equals 104. y equals the square root of 104. And so about 10.2. And for this one, no units, so we'll call it units. It's really easy to look at these. A lot of these will be drawn to scale and see that it's a right triangle. Make sure you ask yourself the question, is it bisected? Then I know it's perpendicular. Is it perpendicular? I know it bisects, so that you can justify what you're doing. That's it for today's video. Thank you for watching. Have a great day.